So, so this is free diving. I think it's kind of a cool video. I took a scuba diving class maybe a year and a half ago, which is kind of curious to know how not to do this, of course, but to breathe with air. And so the first test, of course, is you have to be able to swim the length of a pool underwater, which is 25 yards or 25 meters. It's kind of interesting to condition yourself to do that. It's really quite straightforward once you know how to do it. Most of us can hold our breath for 30 seconds or a minute, and certainly you can train yourself by just sitting at your desk to do that. And it takes you about 30 seconds to swim the length of a pool, so you just have to do it effortlessly. So anyway, so in fluid mechanics, we've talked about the desire to maybe define fluid pressures. We know that when we swim at depth, we feel the fluid pressures rising around us, and we should be able to calculate that for a number of reasons. If you're going diving, you want to be able to know when your watch will break at 100 meters, what the pressure would be for that. Or your GoPro camera would implode apparently at 75 meters. And so these guys actually can hold their breath, I think, for 4 minutes. So free diving is a sport. I guess the aim is to go as deep as you can in the time that you have. You don't quite know the time you have really, because you have to go down, then you have to make the return journey, and so you have to estimate exactly what your endurance is going to be. So anyway, so I think interesting perspective. So certainly we know that as you go down in a pool, and this is a very interesting pool, it's basically a chimney in the ground, right? That as you go down, pressure builds. There's lots of natural places to dive. I was looking at the New York Times this weekend. There's a story about a guy called Yuri Lipsky, a guy who died diving the blue hole in the Red Sea. So this is a karst limestone chimney, basically, that you can see here, that opens up into the sea, which is beyond it, and you go down and through a tunnel 20 meters, and then you're in the sea all of a sudden. And so apparently it's quite disorienting because of the light shining here. And as you go down, as you go deeper, your blood takes on more nitrogen, and there's some kind of euphoria, like drinking, so-called martini effect, that if you get nitrogen in your blood, so there's less oxygen, that you get lightheaded, and you don't make good decisions. And this guy, when he came out of the tunnel into the sea, instead of going up to the surface, he dove down. And apparently his camera, his GoPro, which survived it when he ended up at 100 meters and panicked and took off all his equipment, recorded his demise. And so apparently it's a YouTube video, which we won't show here, but kind of macabre, that basically filmed his death, not death. So in the same way that as you go deeper in water, if you go higher elevation, as in climbing, oh, I don't really want that.
We're from the Kingsman Tailor's shop in London.
That's actually not a bad movie.
Maybe you've heard of
watched
it?
it on a plane. It's an okay. So as you go up in a plane, I wonder if this might have to deal with something on the video. If you put things on these YouTube videos which are digitally signed, then sometimes you get a copyright claim against you. So I don't know whether advertisements would fall in that category. Probably not.
Kind of got a bit of a save the world situation here.
But as you go up in the atmosphere, such as climbing the Hillary Steps on Everest, you know that people on the upper stages of Everest use oxygen. And they use oxygen because the pressure changes. And because the pressure changes, you know through the ideal gas law that pressure is proportional to density. So if pressure drops by half, density drops by half, that means it's half the mass of oxygen per cubic meter to be able to survive. So the reason we use oxygen is exactly that. And so in the same way as if the flight attendants tell you as you go on the plane, these little yellow masks will drop out of the ceiling if you encounter a loss of pressure, hopefully you never do, then all of a sudden that's able to supplement the air that you're breathing so thin. So I guess we're not going to get to the end of this, but I don't know why it went to that all of a sudden, but let's not worry about that too much. And of course, we have fluid mechanics going on around us right now. In what's going on in Houston for the poor souls there, are they getting flooded by a torrential downpour? apparently 20 inches already in some places and 50 inches total predicted in some places of Houston. But we talked last week about the idea of a storm surge. And the storm surge is the height not of the water rising on land due to rain, but the surf coming in off the Gulf. And so what we'll do today is we'll talk about fluid pressures at a point. And these three things, water pressures as you go down in depth, air pressures decreasing as you go up in elevation, and also the storm surge within Houston are all linked in some way, as we'll maybe see as we go down the road. So that's our task for today, is to be able to say something about that. So our activities today are basically this. Fluid pressure at a point. Everyone see? Lighting okay for everybody? So we'll talk about fluid statics. So we'll talk first about fluid pressure at a point and how we define that. And then we'll realize that fluid pressure at a point is controlled, well, not by just that magnitude, but also by the fact that it matters how much height of fluid we have above us, the column. So the reason we feel 101 kilopascals here on us is that we have the atmosphere above us, which reaches to some height, and that's the reason that the pressure that we feel is just due to the weight of the atmosphere. And so what we'd like to do is be able to say something about the magnitudes at which pressure change. So we'll end up developing basically a few expressions. One will be this. One will be that the pressures in the x direction and the y direction and the z direction are all equal. And that the changes in pressures in the horizontal directions are 0. So that's our end point today. That's what we'd like to be able to show. So to do that, we will take a diversion. So anyway, you'll get that. I don't mean to take this off. We'll go through this in due course. All right. So here's the deal. I know I shouldn't take things down as soon as I put them up. Fluid pressure at a point. So we could use the example that we didn't see of people climbing up the Hillary steps to basically look at what pressures would look like on the top of Everest. So if we look at mean sea level, which we'll call elevation of 0, and we look at the elevation at the top of Everest, which is something like 29,000 feet, which is about 10,000 meters. Then one way to calculate the magnitude of the pressure that we see, not if we're standing on the top here, but if we're standing on the bottom here, is just to imagine that we have a weightless container and that this container has an area of, say, 1 meter squared, in which case we know that the weight of this will be equal to the mass times gravity, which is same as the volume times the density times gravity, which is the same as if this height here is z, is just area times z times rho times g. So I guess we don't actually need to assume that this is 1 meter squared because we've got it in here. If we assume that the density of the fluid that's in there, which is air, which is roughly not a meter cubed, but 1 kilogram per meter cubed, which you don't need. Then what we could do is we know that the force that we have to apply here to counteract that is W. But we could also write the fact that W is equal to the pressure multiplied by the area, right? By definition. Pressure is just a weight divided by an area, or a force divided by an area. So if you feel more comfortable writing it as pressure is equal to W over A, that's equally admissible. Then we could also put this equivalency that this is equal to pressure times area. If we know that, bless you, we can get rid of that. And we have just the fact that pressure, probably an expression that you already know, is equal to depth below a surface multiplied by density times gravity, which is the same as depth multiplied by unit weight, because this here is basically unit weight, which is equal to pressure. And so, since we know that at the bottom here, this pressure is equal to 100 kilopascals, we could alternatively figure out exactly what that pressure would be if we know what the density, the unit weight is, and this is. So let's do that. So if we substitute in the numbers for this, that this is equal to 10 to the 4 meters, 10,000 meters. Density is equal to this, so unit weight is equal to 1 kilogram per meter cubed times 9.8 meters per second squared, which is G, right? This is G, and this is rho. Not P, but rho. And if we substitute that in, then we end up with pressure is equal to Z, which is 10 to the 4, times this, let's call this 9.810. So this is 10 newtons per meter squared. Meters cubed, rather. Squared here, meters and meters. So if we work out this, then just by chance, not completely by chance, this is 10 to the 5 pascals, which is equal to 100 kilopascals. So if you're feeling not so sure with your units, then have a look in your text and make sure you feel comfortable with it. So the bottom line is we've gone through this. We've assumed that this is a canister full of air. We've calculated what the weight is and what the pressure would be that we'd have to support that weight. And it turns out to be, just not completely by chance, exactly what we feel here, 100 kPa. And so that's the reason that we feel that weight, although it's not quite true, because we know also from the ideal gas law that pressure is equal to density times gas constant times temperature. So we know that pressure is proportional to density, or density is proportional to pressure. And so if we think the pressure is 10 to the 5 kilopascals here, by definition, the pressure here with no weight above us has to be 0. And so if we plotted the pressure with depth over this particular length, I'm going to have a hard time getting the graph in here, but let's try it anyway. Then the pressure that we calculate would look like this. This is Z. This is pressure. This here is what we feel at the bottom, which is 100 kPa. And by definition, if we did this and cut it progressively at different heights for these different height containers, so the container here is 0 height, so Z would be 0, so by definition this pressure would be 0 as well. And so it means that you go to the top of Everest, great, you have some air as you go up there, it's 1 kilogram per cubic meter that we're assuming. As soon as you go 10,001 meters, all of a sudden you're in outer space and there's no air at all. And so that's not quite the case. And so what we're going to do is we're going to re-examine this. So that's a very simple example that allows us to be able to at least get one important relationship which we have here, and that is this one, which you'll use throughout this class, by the way. And that is you get pressure from the product of unit weight and the amount of fluid above you, basically. And so that's the first approximation we'll make. All right? So that's where we're going with this. So let's do the same example. I guess I do just have enough space here. And so the same example here that we'll try is, let's do the same graph. Whoops. And that is that if we take the same container, that has a height, in this particular case, Z1, we know that we can calculate the pressure here. P1 is equal to the unit weight of the fluid times Z1. We've just done that. And so we know that if we do that, this is pressure, this is depth, this is Z equals 0, this is P equals 0, and this is P1. P1 and Z1. So this is basically one point that we have from looking at the pressure here. If we either make that can longer now, or for instance, let's say we just take a second can and put it underneath and have them both supported on each other, so that now Z2 is equal to Z1 plus Z1, if you like. So this is Z2. Then we know that the weight that we have to accommodate here is just going to be equal to the pressure is equal to the unit weight Z1 plus Z1. It's just double the weight, right, that we have. Same area. And so generically, we can be assured that the pressure we have is just going to be equal to, and we'll use this in the future, some reference pressure plus a unit weight times the difference in elevation. Maybe we'll call it delta Z. So in other words, this pressure at this point here is going to be twice this value. So let me do it this way, because then I can draw it exactly. So this merely telling us that this is now the pressure at P2 due to Z2, and it merely follows that it's just a multiplier. And so we've made an assumption here, actually the same assumption we made for the Everest example, and that is that the density of the fluid doesn't change as you go deeper. And so what we want to do now is come up with a different way of being able to maybe represent that, because that's not always true. So fluids are actually quite incompressible, and so they don't change density very much. But gases do, because we know they do, because they're compressible. And so one thing we could do with this expression, if I roll this up here, is let's take this expression that we have, that pressure is equal to unit weight times depth. Let's say that instead of being absolute, we can just say that it's a change in pressure with a change in depth. And let's say that we define Z as being negative. Minus VE is my shorthand for negative, downwards. In which case we just need a minus sign here. So if we do that, we can just rearrange this as something that looks like this, which we saw when we started out this morning. And that is this expression that says how pressure changes around us. This is always true. It's always true if it's a liquid. It's always true if it's a gas. Both, of course, are fluids. This is only true if it's a liquid, because gas densities change with pressure. And so what this physically means, if you want to understand this expression, really what it's saying, if I use a nice color here, we could write this also as dP dz is equal to minus unit weight over 1. And so we could draw a couple of small similar triangles. One here and one here. Little differential triangles. And if we do this, this then is dz. This then is dP, a small change in pressure with a small change in depth. And because they're equivalent to each other, then this has to equal 1, and this has to equal the unit weight. And so that's physically all that expression means. It means as you go down in depth, the incremental change in pressure you feel is proportional to the increment of depth you go down. And so that's just similar triangles. And so that's the first step on our voyage to be able to understand what's going on. So remember that the fact that this is a straight line is not always true. It could, for instance, be curved, and incrementally at every point on that curve, the dP dz would be tangential, would be the gradient of that curve, but it doesn't have to be a straight line. So let's do something a bit more sophisticated then. Okay, different class. Let's do this. That's, yeah, different class. Capillary pressure diagrams for those of you who are environmental systems engineers or petroleum engineers. All right. So the more sophisticated way of doing this then. So we took a bucket, which happened to be a certain shape. Let's think of a little differential cube. So we're going to choose a coordinate system. And this coordinate system is going to be our right-handed coordinate system. I'm not being rude. X is your thumb. Y is your first finger. Z is your second finger, maybe index finger, right? X and Y are in the horizontal plane. Z is vertically. So this is the sign convention we'll use throughout for this particular class. So this is X, this is Y, this is Z. These are positive magnitudes, so Z is positive upwards, which is the convention we'll always use in this class. And we are going to draw ourselves a little differential cube. I'm getting pretty skilled at this. I'm proud of myself. Okay, and the lengths of this thing in the directions that we draw them would be, this is a length dx, this is a length dy, this is a length dz. We'll make the area of this equal to an area, which in this particular case is dx dy, but we don't care about that. And we will have acting on this some fluid pressures. A pressure acting upwards, a pressure acting downwards, which is slightly modified from the one acting upwards because we've gone up in height, And what else? This could be accelerating in the z direction at some acceleration. Not a velocity, but it's accelerating. So it's not going up at constant velocity, it's accelerating, just as if I'm throwing it up, or as if I'm dropping it down. And is that all we need? Yeah, that's pretty much all we need. So, we said when we started out on this journey that you need one expression. Do you remember what it was? Newton's law. So we can sum forces. Actually, Newton's law is written in terms of forces in x, y, and z, the three directions we've chosen, and has accelerations in x, y, and z. So individually, it's just, this is actually three equations, but let's not worry about that. Bless you. Let's do it for the forces that are applied in the z direction, which are equal to the mass multiplied by the acceleration in that direction. So let's sum the forces that are acting in the vertical direction. Actually, I'm going to stay with this. So acting upwards, there's a pressure at the bottom multiplied by this cross-sectional area, right? There's a pressure at the top which counters that. And let's just multiply this expression by 1. So this is the pressure plus a change in pressure as it gets to the top. And I'm just multiplying it by 1, so I'm not really changing anything. It's acting in the negative z direction. So by our convention, this should be pressure plus a change in pressure with elevation times dz. Times an area. There is a weight acting downwards. It's acting in the negative z direction, so it's going to be equal to minus the volume, which is going to be the area times dz. So this is just the volume of this cube, right? So the area is this total contour here times the height, and it's multiplied by, we'll call it by the unit weight, rho g. And we'll just make sure that we realize which part of F equals ma this is equal to.
I have a quick question.
Yep.
Is your V, is that just volume or specific volume?
Volume. Volume on meters cubed. And so the inertial term will be mass, which is going to be volume again, multiplied by rho, multiplied by acceleration in the z direction. So these are both accelerations. One happens to be gravity, which is pulling us down. The other, az, is an acceleration we're applying to this little cube. And so that's a balance equation. It's no different from having a brick on a table and looking at all the forces that are applied on this. The force of keeping it up, the force of gravity holding it down, any acceleration I apply to throw it up into the air. And so what we can do is we can now start getting rid of terms that we don't like. And so one term, I guess, volume is actually area times dz also, right? So area goes out, area goes out, area goes out, area goes out. This term here, these cancel. And so what we're left with is this term here. So it's minus, I'm going to write it as a partial derivative, so don't worry about that. Minus dz rho g is equal to dz rho az. dz. Yes, thank you. Good to keep track of me. And so we have an expression now which is minus change in pressure with elevation minus rho g is equal to rho az. Or as in this class it's written in your textbook, that's me just, no, I'll write it the same way. I won't change it. So this is with respect to the z direction. If we did this for the two other directions, right? So all we're doing is looking at this moving upward, up and down right now, the z direction. If we now look at fluid pressures pushing something sideways, then because it's going sideways, there's no component of gravity that's acting on it, so we can throw that term away. And so you'd expect that if you did this exactly again for deformation in the x direction, it would look like dp dx minus 0 and in the y direction, this is x rather, and in the y direction, change in pressure with y minus 0 is equal to rho ay. So if we wanted to, so usually you'll see them written in terms of x, y, and z. So this one would actually be down here in that right order. But the z one's a hard one to do because it has gravity in it. The other two don't have it because gravity is perpendicular to them. And any time a force acts perpendicular to the direction you're resolving, it has no impact. And so this term here goes away. And so you may think of it as overkill, but these are basically the expressions that we talked about at the beginning of class. We said that there are three expressions that are important to us. We'll only use, when we're looking at fluid statics, we will use only these first portions. And these are that the change in pressure with elevation is equal to negative unit weight. Acceleration is 0, so let's put these equal to 0 for now. No accelerations in the system. We'll deal with that all in due course. So that's one that we wrote down at the beginning of class today. The second is that the change in pressure horizontally is 0. Because of these last two equations. One thing that we haven't derived, but you might take on trust, is that the pressure at a point, Px equals Py equals Pz. They're equal to each other. So when you go down in a swimming pool, the fluid pressures you feel in your ears are due to the height of water above it, but it acts in all directions, not just vertically. And so the manifestations of these are that, so I guess maybe I could draw a little cube that includes this. So actually, let me draw a picture that kind of explains this. So we know that if we take the surface of fluid and we go down some depth below this, and we'll call that, actually let's call it h, as opposed to confusing z, which is really a coordinate direction, which has direction, with h, which is a scalar, which just has magnitude. We know that if you wanted to calculate the fluid pressure at a particular depth, we could do that quite straightforwardly because we know that pressure is equal to gamma h. So this is pressure. If we went 10 meters from this, and we did the same drawing, that we looked at the pressure and how it changes vertically 10 meters away, we'd find again that pressure is equal to gamma h. And so if we know we're at the same height at each of these places, or sorry, depth, I guess, then by definition, the pressure at these 2 points is the same, right? Because it's varying in the same way as you go in depth. So that observation is no different than this as a statement. This is saying as you go in the x direction, dp dx equals 0. The pressure here is 10 megapascals. The pressure here is 10 megapascals. The pressure here is 10 megapascals. The change in pressure as you go horizontally, there's no change at all. So that's really a physical statement. So this is an important statement for us because we know as we go horizontally, there's no change in pressure. The other one is what we've already done with this, is we can easily integrate this, and we can do, for an incompressible fluid, then we can merely take this expression dp dz is equal to minus unit weight. If we rearrange it as change in pressure is equal to minus unit weight times dz, we can just integrate both sides. If unit weight is constant, we can keep it outside the integral, and we just have, if we do that integration, we end up with P evaluated at P1 and P2 is equal to minus unit weight Z evaluated at Z1 and Z2. And you're close enough to your calculus for sure, you're going to use it in your careers, is that this is equal to P1 is equal to P2 minus unit weight Z1 minus Z2. And I suppose in this it depends where you put your P1s and P2s. If this happens to be 0.1, and well, let's see what we get here. So P, I guess we want, let's do it the other way around. So let's do this as 1, and this is 2, since we've written it this particular way. We want to get the pressure at 0.1, so it's going to be the pressure at 0.2, which is 0, minus unit weight times Z1, which is this point here, minus Z2. And so this point here is minus 10 meters, and this is 0 meters. So it's a function of our sign convention. So if we do this, this is unit weight. Z1 will be equal to minus 10 minus 0 meters, and so it'd be equal to 0 plus unit weight times 10 meters. Because we've used this form, this. And so this, you'll probably, certainly you'll end up using the expression that the pressure at a point is equal to P0 plus unit weight times the change in height. And this is a scalar value which is always positive, and it's the depth below the surface, and this will work just fine for you. So I imagine that you'll use this, and this is what you're used to using. In some calculations, we'll want to use the proper coordinate system that we've defined. And the proper coordinate system is that x is horizontal, y is horizontal, and z is positive upwards. And this expression accounts for that. And so don't let it confuse you. You'll be able to work it out. But this is the correct calculation. It's not erroneous math. I do lots of erroneous math, but today is not that occasion. Okay? Yes?
Can you go up to when you cancel pressure and area, why didn't you not put one side?
Because they're equal to each other.
Right, but is it pressure times area multiplied by the negative quantity then? One side, or is it minus that quantity?
Pressure is multiplied by. This is all multiplied by it.
To the left, like, or are you just showing that's what you cancel right there?
It cancels out with this one. And the only thing that's left is this.
Right, what I'm saying, like, is it pressure times area minus that quantity then?
Pressure times area minus this whole quantity, yes.
Right, so then if you cancel pressure and area, won't there be a 1 minus that quantity?
No, these two pressures are both multiplied by areas. And so when you cancel, one's negative, one's positive, they just cancel out. It's okay. Yeah, just think about it. Go back through the movie. No, I think it's okay. So, perhaps I'm not explaining it well, but I think it's okay. Trust me. Never believe anyone who says that. Never believe anyone more than 25 who says that. All right, what else do we need to do? Well, we got 10 minutes to have some fun, I guess. So, everyone okay with this? It's kind of fundamental. So, this is kind of the expression that you'll use. This is only true for a liquid. We've made this point that this is for an incompressible fluid, which is a liquid. This is always true. We've said that. So let's go back to what we talked about before. We said we'd deal with two particular behaviors. One was incompressible fluids, so I guess we've probably done that. Let's talk about compressible fluids. And we'll go back to the same way of doing things. So for a compressible fluid, it's relatively straightforward. Well, he says, having done it many times himself, but maybe the first time for you guys. So this is the same scale as before. This is pressure versus elevation. This is positive. This is atmospheric pressure at sea level. Our problem is going to be that our pressure, we would expect, would look a bit like this. It would always satisfy this condition that dz dp, or rather dp dz, is equal to minus unit weight over 1 if we want, right? The same construction did. That's absolutely true, even for gas. But we know that pressure for a gas is equal to density gas constant times time. So in other words, the outcome of this is that density is equal to pressure divided by RT. So if we take this expression now and we rearrange it as we want it, so we're going to rearrange it as change in pressure is equal to minus unit weight times change in elevation. We know that this term on the right-hand side is actually gravity times density times dc. And we know that this is this. And so we could substitute this very straightforwardly as minus gravity times divided by RT times pressure. So all I've done is substituted this for this, and that's this and these two components on the bottom. Yes, indeed. Thank you. Glad someone's awake rather than me. And then you do the integration. And so I guess first of all, before you do the integration, you get all your terms on one side. Pressure over pressure is equal to minus G over RT dz. You integrate between, I did it P1 to P2, I guess. Did I do it the wrong way last time? Doesn't matter. It comes out. Z1, Z2. And if you do that integration, then this becomes a log, right? So this is log P2 over P1 is equal to minus G over RT multiplied by Z2 minus Z1. Which allows you to get pressures, and if you exponentiate it, in other words, just multiplied by e to the x, you get P2 over P1 is equal to exponential of, in brackets, minus G over RT, and the distances in elevations, Z2 minus Z1. So the final expression, well, you can see it. So in other words, you can calculate what the pressure at point 2 is if you know what the pressure at point 1 is, and you know the distance between them. I'm just writing out the same expression. So gravity divided by the gas constant for that particular gas times the absolute temperature multiplied by the difference in elevations. Well, I'm not set up to really plot that today. I do have a little routine that allows us to plot it. But basically, you can imagine that this is an exponential term that starts off at sea level and slowly asymptotes to zero pressure as you go up in elevation, which is just like this curve. I'm trying to get both on the page at the same time, for those of you writing things down. So it looks exactly like this curve. It hits, this would be the value that we have at P1. So this would be Z1, and this would be P1. And somewhere else we'd have Z2 and P2. And of course you can change the location of Z2 all the way through up to the top of Everest and beyond and see exactly what the curve looks like, but you can also do it at single individual points. And so if you do that and you allow, for instance, I guess important to note is that Z1 here, if you wanted to do this, Z1 would be equal to 0 meters at sea level. Z2 would be equal to the top of Everest, minus 10 to the, no, positive 10 to the 4 meters, plus 10 to the 4 meters. And P1 would be equal to 101 kilopascals. Gauge, no, sorry, absolute pressure. Or it could be zero pressure if it's gauge. And they would calculate, it would give you the negative pressure here as a result of that, if you'd use that. So you have to be a little bit careful with units. The only important thing to notice is that when we've used these expressions, it does matter, it really matters, that you use the right sign convention for elevation. Z is positive upwards. We're at zero elevation. Everest is at plus 10,000 meters. If you go into 1,000 meters into the ocean, that is at minus 1,000 meters. It's below us. Yes?
So you are saying that R is not 8.014, it's the specific one?
R is the gas constant for that particular gas.
So it's the 8.314 divided by m.
That's the universal gas constant. So you can write the good point. We glossed, yeah. So you can write the ideal gas law as pressure is equal to density, gas constant for that particular gas, times temperature, or you can write it as being equal to density, excuse me, where this is the ideal gas the universal gas constant. I don't use it very often, but it is 8.7, whatever. And this is the mass of the gas, molar mass. So it'd be the molar weight of nitrogen, oxygen. 70% nitrogen, right, in air, small amount of oxygen. So this, in this particular case, would be the gas constant for whatever the gas is, the mixture. Okay. What else was I going to say? That's probably about all I was going to say. Oh, yeah, no. Oh, we've got a minute left. No. So maybe we'll start off next time. So we've made maybe 3 points. One, pressure varies with the unit weight. dP dz equals minus unit weight. The pressure on a horizontal plane is constant as you go across a fluid. dP dx equals dP dy. And finally, the fact that pressure at a point acts the same in all directions. We talked about going up Everest, and we talked about going deep diving, free diving. We also talked about the storm surge, and the fact that the storm surge should have been 12 feet or something in Galveston. So how are we going to use what we learned today to be able to say whether that storm surge could be caused purely by barometric effects, by air pressure? So think about that, and maybe that's the first thing we'll talk about next time.